Okay, good afternoon, everyone. And it's about time. Okay, it's my pleasure to introduce Professor T.P. Ma to give this IAS talk. And Professor Ma is like, as you know, he's a Raymond J. Wean professor of Yale University. And he has many credentials, okay, like some of them including he's a member of National Academy of Engineering, a foreign member of the Chinese Academy of Science, and Life Fellow of IEEE. Actually, his credential is much longer than this. Like it's many pieces of paper. I don't think like I can read them all out. But I think like what I remember about Professor Ma is his contribution to the semiconductor industry. Okay, like he's been like a member contributing many years, and most importantly, he has many students graduated, and they're all in very senior position in major companies. Okay, like in the semiconductor industry, and he has many insider story, which is very amazing. Like which I've seldom heard about. Just like in this. A few hours ago, we have lunch together, and he has already enlightened us, okay, with many exciting stories. So I would like to pass this time to Professor Ma to share with you about his insight about the industry over a long history. So it's about 3,000 years, right? So I'm not sure, actually more than that. I do not know how he can compress all this into 1 hour. So let's see. Let's pass the time to Professor Ma, and let's welcome him.
It's really my pleasure to come back here, actually. But many years ago, I was here when there were only a few buildings, and when many of you probably were not born yet. But it is indeed a pleasure, and I'd like to thank Professor Chen for inviting me. So when he said, would you like to come here to give a talk? And I said, yes. From Stone Age to modern nano-electronics. So some of you asked me, are you really going to talk about Stone Age? Professor Chen already introduced me as somebody who lived in the Stone Age and who knew everybody in semiconductor business. So let's start from the Stone Age. The point I want to make is that historically, the human being lived through the Stone Age, the Bronze Age, the Iron Age. The criterion, I think, was that during that age, the most important material that supported the human life was stone, bronze, iron. So now, based on that criteria, I would say we are in the silicon age, because I think the importance of silicon is no less than any of these other materials. So I'm the advocate for this. I hope everybody propagate this idea, and someday the whole human society will recognize this is the silicon age. All right? So if you look at the number of years, the span of years that these different ages span, everyone is more than 1,000 years. So if you're a historian, you would say, by deduction, the silicon age should last for another 1,000 years, because we are in infancy in terms of silicon age. The first transistor was invented only less than 1 century ago, and if this is the case, then a lot of people say silicon is over. Not so. It's still an infant. So if somebody asks you what profession should I be in, silicon. If you have watched the movie called The Graduate, right? At that time, the graduate, Dustin Hoffman was asking, what should I be working on? Plastic. So I'm saying silicon. If you look around, we are surrounded by gadgets, equipment that would not be here without silicon. Digital TV, digital cameras, smartphones. Okay, here I want to introduce the key element, one of the key elements. Everybody take a cell phone, take a photo out of a cell phone. Camera on a chip. was invented by this fellow, Eric Fossum, my proud student, 1994 Yale PhD. He invented this, and he was receiving a so-called equivalent to a Nobel Prize, Queen Elizabeth Prize, just last December, for his invention of the camera on a chip, CMOS imager. And he showed me the photo. Queen Elizabeth herself was ill that day, but Prince Charles received him. So he had several photos with Prince Charles. And I said, what were you talking about? He said, even though he was a, American all the way, he said, I couldn't understand a word that Charles was talking about. So, but he just nodded and smiled all the way. In any case, he is a huge contributor to our human lives due to his invention of a camera on a chip. Another person, another proud student of mine, Stefan Lai, he invented everybody uses USB, right? And the flash memory, the core memory cell, Flotox, was his invention. So we're also very proud that, and everybody also basically uses USB, if not more than one. And you look at internet, wouldn't be possible without the silicon chip, GPS, Nintendo, electronic game. Don't belittle electronic games. I remember IBM used to be the biggest maker of chips for supercomputers and mainframes, and then gradually they shifted their emphasis to commercial chips. And one group that I was very familiar with told me that they were assigned to work on Sony workstation, PlayStation 4, and said, wow, they used to work on mainframe computers, and this PlayStation chips were a lot more complicated, a lot more demanding than their mainframe computers. So this is one of the drivers of frontiers of silicon technology. And then you have the bioelectronics, optoelectronics, telecommunications, even solar cells. 90% of the solar cell on the market based on silicon devices. Defense electronics nowadays, whichever country has the most advanced integrated circuits, electronics, would have a huge advantage in terms of warfare. And drones, autonomous cars, basically technology is ready. The things that have held back the commercialization of autonomous cars is mostly sociological and legal. So these would take far more complicated solutions, but not the technology. And our society is now heavily dependent on electronics. And I listed a few that you're all familiar with. So electronics is the largest industry in most developed countries, and is also the one with the fastest growing rate. So I have some data to show you. You can see that before the year 2000, automotive industry was the largest, and electronics surpassed it. at around year 2000 with a faster growing rate. And the materials that support the automotive industry was steel. Steel was the largest industry in terms of materials and surpassed by semiconductors not too long ago. Okay. Another interesting graph I want to show you is that the IC industry, the sales volume, is projected to be around 600 billion by year 2022. And the electronic industry is like 10 times. And the information industry is only 5 times. And the total GDP is only a few times of information industry, right? So you can see this importance of integrated circuit and electronics. So again, if your students or your offspring ask what profession should I choose, information technology based on silicon. The foundation of the electronic industry, semiconductor technology. Here we take a 4-function calculator and take it apart. You can see that the brain, the heart, is just a small chip. And this chip comes from a wafer, silicon wafer. This is a bare wafer, featureless, and after hundreds of processing steps. Oh, by the way, you have this person here, dressed like a spacesuit. It's not to protect him. This is to protect the wafer. All right, so because human bodies emit a lot of contaminants. So you have to really, in a clean room environment, you want to wrap the operators around so that the wafer will stay clean, not to protect the body. After hundreds of steps, as I said, chips will be fabricated on these wafers, and you take a microscope view, you begin to see these features, but it takes a much higher magnification to see the interconnect lines on the top, and you will realize this is certainly a lot more complicated than even the maps for Hong Kong, which is quite complicated. Then you want to look at the details. You can't do it with optical microscope, so you use electron microscope. And here is a view from the top. You can see the copper interconnect lines, but the transistors are underneath and a lot smaller. You can't see it, so you need a higher magnification electron microscope. So here you start to see this interconnect, the feed-throughs that connects to the transistor. So you barely see transistors underneath. To really see the transistor, you need, this is by scanning electron microscope. So you need transmission electron microscope to see. This is based on 65 nanometer technology, which is pretty ancient because nowadays 10 nanometer fabs are making wafers in the mass production mode, and 7 nanometer is almost ready for your next generation iPhones. So you can see even the 65 nanometer technology produces channel length of only 30 nanometer. Vertically, there is one critical layer. It's the gate dielectric. At 45 nanometer node, the gate dielectric, gate oxide, SL2, has a thickness of 1.2 nanometer. The reason I showed this particular graph is because this is a critical thickness. SL2, its usefulness stops at 1.2 nanometer. In terms of production, one could not go below 1.2 nanometer because of the leakage current. It's because electron tunneling now becomes a big factor that causes too much power, standby power, even though in the laboratory one can make a much thinner gate dielectric. Now let's get back to the first all-electronic computer, right? This computer was based on vacuum tubes as their logic gates. There were 3,000 of them and occupied a large room, air-conditioned, again, not to cool the people, but to cool the machine. And compared to the previous computers all based on mechanical moving parts, this all-electronic computer was very fast in the end of 1940s, early 1950s. This was used to compute the trajectory of guns. And they were very fast on a relative scale. Unfortunately, the reliability wasn't too good. So on average, every 10 minutes, a vacuum tube will blow out. And all these operators will frantically try to find where the blown vacuum tube was and then replace. So you can imagine only a few thousand vacuum tubes, and the reliability was only, in terms of lifetime, only 10 minutes. So you can see, in my lab, I actually had this original one flip-flop, one gate, based on vacuum tube. And you can see every gate had to have its own transformer. So these were more than 10 watts per gate, all right? And if you had in your iPhone, same number of gates, you can imagine how big this would be, because in your iPhone you had tens of billions of gates. And if you had to power up your iPhone, so the entire electricity of Hong Kong would not be enough to support one iPhone. All right, so that's the progress that we've made. Now came the first transistor. It's a very famous picture. It's due to Bardeen, Britain, and Shockley, 1948, at Bell Labs. You can see that, this is like a twisted wire or something, and then they had a point contact. And at lunch, we talked about this famous picture. Shockley, actually, Bardeen and Breton, these were the two engineers, physicists who discovered the transistor. But Shockley was in Europe, but before he left, he told the two, because they were working on this so-called transistor, and said, don't tell anyone if you saw this transistor effect until I'm back. So they telegrammed. There was no fax, there was no email, and they telegrammed Shockley and said, Eureka, we found the transistor effect. So it's okay, don't tell anybody until I'm back. So he came back, and he called this huge news conference, and with New York Times, Wall Street Journal, Time Magazine, or Science Magazine, all these. And this was the famous photo. He was just behind the bench, looking under the microscope. The two actual inventors were seeing, right? So naturally, this gave the impression that he was the chief inventor. So indeed, later on when the Nobel Prize was announced, all three of them were the Nobel Prize winners. So the moral of the story is that if you're a group leader, you had a chance of getting Nobel Prize, make sure you have this photo up that you look like the leader. But that's not fair, actually. He really deserved it, Shockley, because the two of them thought the transistor action was due to field effect. He was the one who actually developed the theory for the bipolar transistor. So he really deserved it. Then came integrated circuit. Jack Kirby, 10 years later, slapped together a transistor, a capacitor, and resistor, glued them together, and made an integrated circuit. So filed for the patent. This is a page of the patent. The patent certainly looked a lot more like an integrated circuit. So same year, Bob Noyce, he filed for a patent, planar IC. This is actually more like the building block of today's IC compared to Jack Kirby's slapped it together, although he was the first one who named this integrated circuit. So year 2000, the Nobel Prize was announced for the invention of integrated circuit. Jack Kirby got it, not Robert Noyce. Who? Why? Because Robert Noyce died before the announcement. So that's another moral of the story. If you have a chance of getting Nobel Prize, be sure not to die. Be sure you have good health, all right? Just like we had a chemical engineer who got a Nobel Prize for chemistry. He invented this large molecular mass spectroscopy method. And he went to receive his Nobel Prize, and he was able to invite 24 of whatever he wants to invite. So he invited his former students who helped him do the research to get the Nobel Prize. He almost didn't get it because he did receive the Nobel Prize the next day. He got heart attack. And actually his student was the one to deliver the Nobel speech. You know, usually there is a lecture for the Nobel Prize winner the next day to deliver. He wasn't able to do it, but his student had this honor to, and you can look it up. You know, it's a video record of his student delivering the Nobel speech. But he survived. He didn't die. Okay, after this, the very important development was the 1K DRAM, Intel. Intel was in the DRAM business. Probably many of you didn't know. Most of you probably didn't know. I want you to look at 1K, 1 kilobit DRAM at that time cost $21 per chip. All right, for 1K DRAM, $21. Then came 16K, again Intel, $33. 64K, $47. All right, the 64K has an interesting story. It's a turning point for Intel because a very smart engineer, said, based on his study, 64K is the end. DRAM can no longer be integrated better. You cannot make DRAM cells smaller than this. Why? Well, he discovered a thing called soft error. In other words, from time to time, some places will have 1 become 0, 0 become 1. And that what he attributed to alpha particles. It turns out that the packaging material that they used, metal packages that contain a lot of heavy metal. Heavy metal would have some isotopes. These isotopes are not stable. They decay, emit alpha particles from time to time. Every alpha particle will hit many cells. Along the way, the memory state will flip. So based on the calculation, if you have too many close together, then you cannot recover it. And therefore, the soft error rate is too much. So Intel bosses were all physicists, engineers. So they understood. So it's, we will shift. We will no longer make DRAMs. So they started to do microprocessor. The Japanese, they're far behind in DRAM. First of all, they didn't see this effect. Secondly, they did not understand the paper, so they kept doing 64K, 256K, 1 meg, nothing happened. So it turned out that the Japanese at the time, they were known for making things cheap. So instead of metal packages, they were using plastic packages. There was no heavy metal, there's no alpha particle. So they kept going, and they overtook Intel, became the kingdom of DRAM. And for many years, they were the top 10, at least 7 companies, Japanese companies, became the top 10 semiconductor companies, all due to DRAM, all right? But Intel, they went to microprocessor. It turned out they made a very good decision based on the wrong reasons. Microprocessors became very, very profitable, a lot more profitable than DRAM. And DRAM became a cutthroat business and cyclic. Sometimes they have huge profit, and sometimes they lose their shirt. And many of them join so-called billion-dollar club. What does that mean? They lose $1 billion per year. So many of them, and finally, Japanese semiconductor business is almost zilch, and the Koreans took over. They still had a lot of government backing, and so they're still dominating in the memory. But Intel enjoys microprocessor dominance, and this is the first 4-bit microprocessor, 8-bit, P-channel, N-channel, 8-bit, 8080. But the next one, 16-bit. This was the first one used in IBM PC. All right, that's another historical development. And from this point on, many of you who are as old as I am or slightly younger remember these designations. IBM PC 286, all right, based on Intel's 286. 386, based on Intel's 83. You can see the number of transistors keep going up exponentially. 486. By that time, people say, well, you Intel people, you have no imagination. 286, 386, 486, get something fancy as a name. So Pentium, all right. Fine, right? That shows that they had some sort of, instead of just this numerical sequence, they had some imagination. So, okay, that has more than 3 million transistors. So the next one, they ran out of naming contest, Pentium Pro, 5.5 million transistors, Pentium 2, Pentium 3. So these engineers don't have imagination. So I would recommend that universities like you guys, Yale, we should produce engineers who have imagination, who can write a full sentence. Pentium 4. All right. The progress of the semiconductor industry in the last 5 decades followed the Moore's law. What's Moore's law? Moore's law basically says the number of components on a chip doubles every 18 months. As along with it, the speed, cost, reliability, everything improves exponentially. And when did this is Gordon Moore, he's co-founder of Intel. When did he publish his Moore's law? Right around here, 1970. Based on just a few years, less than a decade of observation, he looked at the number of transistors on the available commercial chips. And this was the data. So he just drew this straight line on this logarithmic scale and said, this is the Moore's law. He published around here. Not many people actually paid attention. Until 10 years later, he revisited again. And this was the line he drew. And these were the data he collected. So indeed, experimentally, what's going on conform to his Moore's law. So he published another one in a more reputable journal. And at that point, people took it more seriously. So everybody believed there was such a thing called the Moore's law. And every company in their strategic plan would say, well, everybody else will be here, so we must be here or better. Otherwise, we'll be left behind. So that's the origin of the Moore's law. And if you look at now, many different technologies, different products, basically follow this exponential law. And as a result, on the tip of a ballpoint pen, you have 10 million transistors. Now, one interesting illustration would be the DRAM development. Remember 64K, right? This was the end, according to this Intel engineer. But the Japanese didn't buy it or didn't understand, just kept going. 64 kilobit, basically on average, can store 1 page of information of a book. Then 4 meg would on average store a book's worth of information. And 1 gigabit, one entire encyclopedia. I think the young people don't know what encyclopedia is. They used to be in USA a profession. You have encyclopedia salesmen would take a volume and go to your house and knock on the door. We'll give you this first volume for free, plus, give you a nice cup or some utility stuff. But you sign this thing and we'll send you the second volume, or your kid will definitely depend on this for their homework, for research, and whatever. So most families, middle class or better, will have bookshelf full of encyclopedia from volume A all the way to Z. And we still have it, but mostly for display. No one uses these encyclopedia to look up information. Everybody goes online. But nonetheless, 1 gigabit was able to store all the information in the encyclopedia. That's Moore's law. This is also the speed increases exponentially. And the IC cells, that's another Moore's law, increases exponentially. And this is all primarily due to the fact that the feature size of the components, especially transistors, decrease exponentially. And for this, this is when I started to research on semiconductors. It's 10 microns line width. Nowadays, as I mentioned, 10 nanometers, all right? And you can see this reduction, amazing within the past few decades. It's many, many thousands fold. And now if you look at, to put it in perspective, look at the DRAM cross-section. Before 1 megabit, it's all planar. In other words, the DRAM consists of a transistor, which is a switch, and a storage capacitor. So before 1 megabit, it was planar. The transistor and the storage element could be made on the same level. But after 1 meg, the storage capacitor, you have to have enough capacity to store enough information. So, but we are shrinking the area for each bit, for each new generation, and therefore you need to go 3-dimensional, just like you don't have enough land in Hong Kong. So in order to get more usable space, you go skyscrapers. That's one approach. Another approach is dig down many, many levels of basement. And these two were competing for quite a while. The IBM led camp like the trench approach. The Japanese like the stacked approach. This was one example when I took this photo to make slides. 64 meg at the time it was the leading DRAM, but now there's no one actually makes 64 megabit. But even for the 64 megabit, nowadays it's very primitive, but you look at how complicated. Each bit consists of a transistor plus the storage capacitor. The storage capacitor, you look at the aspect ratio. You have to dig a hole that you have many times the size of the hole in terms of depth. You have to get the stuff out. And then you have to oxidize the wall of this trench. And then you have to fill it in with conductor. And this conductor has to be connected to the transistor. And you can't have pinholes, you can't have broken or shorts. Very, very difficult. But guess how many dollars you have to pay to get 1 bit? Microcent. 1 penny you can buy a megabit. The number of processing steps also increases exponentially. That's another Moore's law. Cost of the processing equipment used to be when Shockley and C.D. Saw, they set up first fab before the Fairchild semiconductor company. They could do it more or less in their garage or basement. Nowadays, just one photolithography machine, such as the one that recently ASML agreed to sell to SMIC, costs over $100 million per machine. And in order to be viable for production, you need at least a dozen of them. Just the photolithography machine alone will be more than $1 billion. Okay, so you can see the exponential rise. So no way one could form a fab in their basement or garage. So you have to have very deep pocket. Either you've been already in the game that's made a lot of money, like Intel or TSMC, or you have government, like China. They wanted to do it, so 100 million is nothing. Okay, so per fab, this was amazing already, 3 billion before 2010, but now, if you look at the 20 fabs that are being built, the average cost is 6 billion, and one of them in Wuhan was 24 billion. So that's the amount of money. However, even with such heavy capital investment, the per unit, per function cost is dropping exponentially. That's amazing. That's why if you have enough money, this looks very attractive. So cost per function, it's Moore's law. It's going down exponentially. And let's look at the DRAM again. Remember, I asked you to, this is plotted per megabit of DRAM storage. When it was first introduced by Intel, it cost, remember 1 kilobit cost them $21, right? So to get 1 megabit, you need $2,000 some per megabit. Nowadays, extrapolate this down, a megabit will cost a fraction. It's a micro penny, right? When we were little in USA, my children were little at least, you could go to many places, put a penny and get a gumbo, a bubble gum, 1 penny, right? Now you have to put 2 quarters to get a bubble gum, but you can get a 1 megabit DRAM with 1 penny. So that brings me to this pi rule. Simon Z is a pioneer in semiconductor textbooks, at least. He observed and introduced this pi rule. That is, the cost of a DRAM chip will drop below pi dollars after 3 years. 3 years is more or less the cycle for the next generation of DRAM that will come out. So remember, the first 1K cost $21. By the time the next generation, which is 4K, was introduced, the first 1K, that's 3 years later, 1K would drop down to below pi dollars. And then 4K was first introduced over $30, but then 3 years later is less than pi. And this, I only stopped at 64 meg, but right now at 64 gig sampling, go down to below pi dollars. So why pi dollars? Well, if you say below $3, $3 rule, this is, no, but if you introduce pi, it's very scholarly. There must be some mysterious integration that gives you this pi. So very clever, becomes a very, very believable rule. Okay, now, if we compare the development of integrated circuit with the automotive industry. If automotive industry had other mechanical engineers or auto engineers, if you are an auto engineer, automotive engineer, you should be ashamed of yourself because you haven't really made much progress. Automotive industry had been making the same progress as the semiconductor industry. We should expect every car to cost 5 cents, have a speed of 40,000 kilometers per hour. You can go from Hong Kong, cross the bridge to Xinjiang, and then back. Have gas mileage of 3,000 kilometers, right? So more or less 1 gallon, you can go to Xi'an and can carry 2 million people. So you only need a few cars to carry the entire population of Hong Kong, right? So that's the dramatic. Or people say, well, we have made improvement. Look at the autonomous cars, and these are due to integrated circuit. Only progress is due to integrated circuit. Okay. So this is a good place to have questions and answers because the next segment will be a little bit more device physics oriented. And any questions, comments?
The recent IT and fintech technology, like AI or blockchain technology, how they are going to influence the device technology?
Yeah, good question. All of these based on computing machines. So the computer machines, the foundation is integrated circuit. So even though the news reporters, they attribute high tech to Facebook, Google type of things, Amazon, they call these high techs. These are applications of what I call real high tech. That is the integrated circuit. So all these will have to depend on, if we stop evolving, they will have a hard time really getting to the destination they really want. Okay. Okay, so now a little bit of device physics. First, we need to take a look at this model transistor, MOS field effect transistor. We should pay attention to the channel length because that's where the current flows from source to drain, and the channel width in this direction, and then also the gate dielectric thickness, because the intrinsic speed of switching speed of a MOSFET, MOS field effect transistor, is proportional to the drain current. All right, so that's why a lot of the development has to do with increasing the drain current. So the drain current, in turn, depends on width to length ratio. So a big effort has been to reduce the channel length and increase the capacitance of the gate. Capacitance, on the other hand, is inversely proportional to the gate dielectric thickness. So there's been a lot of effort to reduce the gate dielectric thickness, and of course the mobility of the carriers. And so these are the key parameters that we are focusing on in terms of device scaling. So here you can see that gate length is reducing for every new generation of transistors, and the oxide thickness was also reducing. And I put a stop right here because at 90 nanometer, the gate dielectric used at the time, silicon dioxide, already reached 12 angstroms, 1.2 nanometer. If you recall, I told you that this is the critical thickness. Beyond that, it's not practical for commercial application. So here is the same transmission electron microscope that I showed you. 1.2 nanometer is from 90 all the way down to 45. 90, 65, 45 all had the same SL2 thickness. And this is due to the fact that this thickness is no longer an insulator. There is a quantum mechanical tunneling that allows electrons to go from the channel to the gate, and that's a leakage current, and that is no longer tolerable beyond this thickness. So this was Intel's warning projection, and in fact, if you look carefully, the microprocessors clocking speed stopped increasing. It used to be increasing exponentially, but at this time, 90 nanometer node, clock speed doesn't increase because the leakage current was too much, right? How come these operating speed of microprocessors keep going up? Heard of multi-core? In other words, instead of one core, you have parallel cores to increase the total system speed, right? Not the transistor. And this is due to the fact that this is the insulator we're talking about. Electrons can tunnel through with a high probability, and that gives you leakage current. All right, so the projection that Intel put out was this exponential increase in the per chip power. You can see this is 1200 watt per centimeter square. All right, if you had experience with changing light bulb slightly after it turned off, and that's a 60 watt light bulb. If you calculate the per centimeter square wattage, it's only less than a single watt per centimeter square. Here you're talking about 1200 watt per centimeter square. So this is a scary scenario that Intel put out. Basically said, if you let the thickness of gate dielectric shrink without doing anything, you would expect at this node, the chip temperature will be same as a hot plate. And then here it will be more like the temperature of the nuclear reactor. And over here it will be the rocket nozzle. And then here is the surface of the sun temperature. So this is provided you didn't do anything to correct it. And some people who are working on solar cells are great. You know, we have a natural source of energy right here. We just harness this energy. But in any case, remember, C is the one we want to increase. So decreasing oxide thickness was the one that we took. But there is another variable, that's the dielectric constant. So we cannot decrease this, we can increase that. And that's the high K gate dielectric scenario. And we're happy to say that our group was one of the earlier ones that introduced this concept. But in any case, it took more than 10 years for the first commercial company, Intel, to really implement this high K gate dielectric. And their news release said, this is Gordon Moore actually said its biggest change to computer chip in 40 years. So that says a lot. And because of this implementation of high-K gate dielectric, when the scaling was more or less stopped here, now we are comfortable that this scaling of silicon-based transistor would go at least to 2025. Okay, so beyond 2025, what do we do? Well, remember this mobility could also increase the speed if you increase the mobility. So people look at these various so-called high mobility materials, carbon nanotube, graphene, 2D semiconductors, 3-5 semiconductors. No time to go through much, but at the Shenzhen conference that I'm going to, I will give a plenary talk on this. So I can only here say a few words. So first, carbon nanotube. And for various reasons, many of us do not think that carbon nanotubes will succeed silicon as the mainstream CMOS transistor material, unlikely to succeed silicon as mainstream CMOS channel due to various reasons, right? It may have some niche applications here and there, but not the mainstream due to this. You're interested, we can talk. Then graphene, we evaluated, and finally we found that, again, graphene is unlikely to succeed silicon as a mainstream CMOS. Again, there will be analog applications as conductors, as barriers for Schottky diode, and things of that sort. Many good applications, but not mainstream CMOS channels. Okay. Then 2D semiconductors beyond graphene, and again, for various reasons, it won't succeed silicon as the mainstream CMOS technology. The most likely, within the time frame we're talking about, will be 3-5 semiconductors. And there are many barriers to actual commercial implementation, even though all these could be solved by hard work and a lot of effort. Unlike the other three, they are at the moment unsolvable problems. So again, I'm not going to go beyond this, right? Please, they can register at your conference. And okay, so next one. Hopefully, because I had made a presentation to all Chinese audience, I didn't have the English version. But basically, I'm going to report the IC industry's current and future possibilities in China, in mainland China. All right, that doesn't include the TSMC and other semiconductor companies in Taiwan, which is, to me, part of China. So we call it mainland China, okay? Okay, so in mainland China, the communications equipment, like a Zhongxin Tongxin, right? Recently, that's a big application, Huawei and Xiaomi. Personal computer like Lenovo, consumer electronics, all kinds of applications developed by people in Shenzhen, for example. A lot of 山寨产品. But they're, in terms of numbers, dollar amount, huge, and increase very, very rapidly. In the last 10 years, the Chinese consumption of integrated circuit increases by 20 to 30% per year. Very, very rapid increase. On the other hand, the total consumption of Chinese integrated circuit, Chinese consumption of worldwide integrated circuit was 200 billion US dollars. It's 45% of the entire worldwide production, all purchased by China. But in turn, the Chinese consumer electronic products, personal computers, and telecommunications equipment, they represent a huge economic sort of help the Chinese development economically. But there's still the fact that 45% of the worldwide integrated circuit production came to China. A huge demand here. Again, I said consumer electronics, computing machines, telecommunications equipment, and automotive electronics. And the thing is that because of the huge demand, the number of dollars that the Chinese produced ICs can only supply in terms of number of dollars so much. But the demand is much increasing much faster. So the deficit in 2007, last year, deficit was 200 billion US dollars. And this becomes a thorn on the back, so to speak. Chinese government really wanted to shrink this deficit. And three special characteristics of Chinese IC market. It's the number one in terms of the volume consumption, number one in the world. And increasing, the speed percentage increase per year is also number one in the world. And the deficit of IC, the sales versus purchase, import versus export, is exceeding any other sector. Recently exceeded the oil, petroleum import, 200 billion a year, and it's increasing that gap. So 2014, the Chinese government, several agencies headed by the Wean, headed by Li Keqiang, right? That's the premiers. They called for, also including the Fagaiwei Science and Technology Ministry, Financial Ministry, many industry and information industry ministry, they together said we need to really do something. We will inject 120 billion Chinese yuan, and with the local government contributing almost as much, and primarily to build new IC fabs. Okay. Although I actually went to suggest that they should take a small percentage, only a few percent of that, to do basic research in IC so that you have a long-term prospect, which was not taken very well. So they just try to have a very, very rapid return. That was the explanation given to me. 业绩, they need next year, 2 years from now, otherwise, their heads will be chopped off. And that was the goal. By 2020, China should produce 40% of what the country needs in terms of ICs. And then 2025, they should produce 70%. I had no idea how they got these numbers. Basically just throw dice or Moore's law. But Moore's law was reality, but this is, so what happened? 2020, 3 years from now, they have to get 40%. Right now, they only got 12% compared to just a year after they made the announcement, increased by 2%. So now they extrapolate, they can never reach this goal. And this is a generous projection by IC Insight. So they may get 20% by 2020, which they will probably revise it downward. But nonetheless, there's a lot of activity building fabs. There are 20 or so, either broken ground or being planned, and many, many cities all had activities of building new fabs. As I said, average fab cost was $5 billion US dollars, and one in Wuhan was $24 billion US dollars. But the ones that actually already built and actually realized what they were saying was Intel was foreign. Samsung in Xi'an, Intel in Dalian, TSMC in Nanjing, etc. What they planned, they actually deliver. The China thing, to me, it's sort of an illusion. Okay, these are the details. Just recently, because of I believe, Zhongxin Communications, the Chinese government announced 3 times the investment, 300 billion. And seemed like this time is real. They really want to make sure that Chinese will catch up with the chips. If you ask my opinion, I would say unless they correct all these, it will be, again, a huge waste of government funding. First is very short-sighted. The government look at this thing as something that can be solved just by throwing money. Also, all the people who are in charge, they want to get visible results. And it's the system that encourages people to get very, very short return. And so-called experts, I know many of them, they don't really understand IC chips. And somehow they got the position to evaluate others, and they dispense funds. Many of them are, we call it 裁判兼球员. They are the ones who apply for fund, and they are the ones who are evaluating their own proposal. So naturally, they got the first big chunk of funds. And the same group of people, they have caused the huge problem that China faced. You say, well, we have not really supported IC industry for many years. not true. If you look at the number of dollars the Chinese federal government that has invested in IC, it's far more than what the US federal government has invested for the last decade. That's very, very clear. And when you say there is not enough investment from the federal government, if you're out investing the US, why do you still say we don't have enough investment? It's not that you don't have enough investment, it's the wasted investment. And all these so-called experts, I also mentioned, they are the judges and they're also the players. All right, so there are many good ways to solve these problems. The thing is, when it comes to their own interest, they will not give up the position that they're in today. And all these new fabs that they're built, they're behind the worldwide leading companies by 2 to 3 generations. Okay, so the summary. In the last 5 decades, the development of IC technology has followed the Moore's law, and silicon-based CMOS technology will continue until 2025. After that, new transistor materials will gradually supplement. I say supplement, not replace. You cannot replace, as I said, silicon still will last 1,000 years. Why? Any new material, like 3-5 compound, 2D transistor materials, graphene, whatever, you need to be able to grow it on silicon. Silicon is the only substrate, affordable substrate, that has now 12-inch and 18 inches being demonstrated, and that's economy. All right, you have to have price competitiveness to go along. If you rely on 3-5 semiconductors without growing on silicon, the biggest is 6 inches, right? And we can discuss the reason why you need silicon. And therefore, I think silicon will be here, even though you use some other materials for transistors. China is the world's largest consumer of ICs, but mostly rely on import. In 2014, China established this 100 billion national grant IC fund, 大基金, has been primarily been used to purchase technology and build fabs. This year, they announced even bigger fund to the amount of 300 billion. This is only the central government, and the local government will match and make it a huge fund for IC development. Over 20 fabs are being constructed, and there'll be a shortage of talent, of people in this field, huge shortage. They're trying to get people from Taiwan, from I'm sure from Hong Kong, and so this is a great time to enter this profession. We have a great impact on the global IC production. So this is what I prepared to talk about, and I welcome comments and questions.
Trade war between Trump and China, then how will one of the vulnerability of China would be the IC industry, then how do you think that China is going to compensate for this situation?
How would would China compete?
Compensate for the situation, because one of the problems with the deficit that you just spoke, US is one of the biggest producers of the world, right? So then Trump can easily target China on this point, right?
Well, in April, Trump and his protege actually announced that we will not supply chips to Zhongxin Tongxin, and immediately Zhongxin business was almost choked off. But then further discussion caused Trump to change his mind. So right now, he only demanded some fine of $1.3 billion, and then you have to change your leadership. And then U.S. will have people monitoring the situation. So that's the new. Who knows? Trump may change his mind again, but that's the recent situation. So right now, the high end of IC, China has no say. So when U.S. said you can't buy from us, and they may go to Europe for some, and to Korea, Samsung for some others, but those all take time. And Trump will also retaliate if Korea said, I want to sell to replace your chips. I don't think Samsung would do that. Europeans maybe, but they don't have really very advanced fabs. They're not a major player in this thing. So right now the situation is, China will have to, if they want to preserve Zhongxin, and Huawei was another one they were talking about. It's even bigger. It also depends very much on, in terms of high-end chips, depends very much on U.S. supply.
Professor Ma, thanks for the talk. It's excellent. Put all this together and have the vision that silicon will have another 1,000 years, which is very encouraging news. I think semiconductor industry is such a huge production in the ecosystem. So I think from Hong Kong's perspective, do you think we have the chance to become the world leader in IC design, even though we don't have the world-leading fab? And because I think from the size, from the land cost, and all the potential hidden costs, I think fab is not a solution for Hong Kong, not even in the loop in the future. Even Shenzhen doesn't have the fab, if you look at the cities. So my question is, do you think any region, not necessarily Hong Kong or anywhere in the world, there's a chance to develop the best IC technology, but without the leading foundry in that region?
Well, very good question. In fact, Zhang Rujing, who founded SMIC, initially he came to Hong Kong before he went to China. And he wanted to create a Silicon Harbor in Hong Kong. I knew this very well because he and my former student, Clarence Dunn, together founded Sida Semiconductor. It's a foundry in Taiwan. He was at TI. And it did very well until TSMC purchased them. And TSMC kept all of the employees and gave TSMC stocks, except for Zhang Rujing, Richard, and my former student, Clarence, chased them away. So Zhang Rujing was very angry. So he wanted to someday overtake TSMC. So he and Clarence then came to Hong Kong. Many of you don't, most of you probably didn't know this. So he actually negotiated with the Hong Kong government. They got almost everything. They got the land even, which then became the software park. And one thing that the Hong Kong government did not agree was they said everywhere we went, all the government said the first few years, all the imported equipment, everything tax-free. Hong Kong said, well, our tax is the world's lowest, and we cannot set a precedent for anything tax-free. We have the lowest. So that's the point that was stuck. Two sides could not agree. So Zhang Rujing came to China. And I was involved too. I didn't know he was, because there was year 2000 when the Minister of 信息产业部, the information technology industry, Wu Jichuan, invited a dozen or so of our so-called worldwide IC expert to have a meeting about whether China should have 8-inch and 12-inch fabs. And Zhang Rujing represented the Taiwan industry. And we didn't know he was already discussing a fab in China. So we said, whatever we recommend will not be adapted. So just a formalism to show that they collected all the worldwide IC experts. And so we recommend anyways. We said you should have tax-free zone. And Zhang Rujing was also there to try to influence us. After all the recommendation was made, we said, okay, this is it. Nothing will be heard again. Very soon, half a year later, all of our recommendations were implemented. Then Zhang Rujing was the one who established the SMIC company. Now, why did he not succeed? Why would he? He got a lot of people from TSMC, from TI, and because TSMC at that time changed their stock option policy and no longer enjoyed, if anybody is interested, it was a huge benefit for the employees of TSMC. But that year, they said, this is no longer affordable. So Zhang Rujing said, I'm going to continue TSMC's practice. So you will all be millionaires in a couple of years. So got a lot of TSMC people, TI people, but he has never made profit. In order for that stock option plan to be implemented to benefit employees, the premise is you have to make profit because it will take certain percentage profit for bonuses. He never made profit. Why? He wanted to build new fabs. His speed of building up new fab was unprecedented. And so all the money he made put in the new fabs. So on paper, he was always losing money. And finally, the investors, mostly government, Datang, and they said, we can't just wait here until you make money. So he was kicked out. There was also the problem that he was from Taiwan initially, and he had an internal group from Taiwan. He was a Christian. So he also had an internal group who were Christian. those are from Taiwan too, because the mainland people seldom had religion. So all these were reasons for him to be kicked out. Unfortunately, if he had just followed the regular commercial kind of a pathway, it would have been very different. He would have attracted a lot of private investment and very little government control. Unfortunately, he had to rely on government to tell him how to run foundry business.
Hello, Professor. Thank you for your briefing about the past and the future of the silicon industry, not only the technology, but also the market. And since you mentioned in the presentation, you say we university have to develop the students with imaginative ability, right? So my question is that from your presentation, basically your focus is on the solid state electronics. So my question is, what's your idea about the flexible electronics and even some liquid metal, some other shape of the electronics? That's all. Thank you.
Yeah, certainly. I think many new applications have been developed. Internet of Things, all these related to, say, well-beings of human beings, wearable electronics connected with all kinds of measurement gadgets. These are all very promising that require flexible electronics, thin film transistors, but these are, relatively speaking, niche market, right? Niche market, how about $20 billion a year? To most industry, that's huge, right? But compared to mainstream CMOS, which is 600 billion, that's still niche, like 5%. But it doesn't mean that you shouldn't do that, because that's still, in terms of applications, in terms of all very important. But I'm only emphasizing on the mainstream CMOS technology.
Hello. About the National Grant IC Fund in China. So is this fund only based for like building fabs, or like what is the exact distribution of like expense for this fund by the government?
Right. In 2014, when I heard about this huge funding for integrated circuits, and in newspapers they say this time we'll make a change. Won't be like the old practice. China will have its own technology. So after, during the discussion, he had a couple of technical people with him, vice president, and they all, seriously took notes, and I was very happy. Toward the end, he said, Professor Ma, I have to tell you honestly that we don't have time to do this. Our leaders said you need to show results next year, 2 years from now. I said only 2%. No, they don't have time to think about the future, because their promotion and races would depend on next year's results and 2 years' results. Therefore, what's the quickest way? The first thing they tried to do was to purchase Micron. Micron, the biggest DRAM company in USA. They almost succeeded. They went to purchase shares from private owners. And somehow this got the attention of US government. And they said, wow, if they succeed, then they lose this largest memory company, plus US government military defense electronics memory-based, memory-related products are from Micron. So immediately they put a stop at this and said, no, this you cannot buy. So what they did was they bought actually still a substantial design company, Zanxun. They bought it. And they were trying to buy others, but then already got the attention of US government, so it's harder. So it's okay, next best thing is to build fabs. And it's easy in terms of hardware, get the building and get the equipment, and very hard to get people. And they are facing a lot of problem to get people, real, not anybody, real talented people to run the fabs. So that is the worrisome part. And in this business, if you put your equipment in and you don't do any production in 3 years, it's depreciated. Becomes very, very not valuable because there's a new generation coming out. So the economy is very different, right? If you make shoes or you make bread, and if the cost is more than what you can sell for, right? If you require $1 to make a loaf of bread, you can only sell for 50 cents. In most industry, you will not make the bread, right? And wait until the price is better. Not in semiconductors, because the biggest cost is capital investment. And let's say you have $5 billion. In 5 years, this is depreciated to nothing. That means no matter what, whether you make it or not, it takes you $1 billion per year to run just the capital cost, right? And that's why, even though you're losing money, you still make the chips. Because if you don't make it, you lose $1 billion. If you make it, you can sell for 500 million. You only lose 500 million. And the consumer benefit, right? The price of flash, price of DRAM goes down quickly. It's not, even though the companies are losing money, they're still making it because they lose less. If they make it, they sell them. If they don't make any, they lose more. So it's a very peculiar economy. So that's also the one that sustains the Moore's law and sustains the pi rule. You know you're losing money, you still make it. You make it, you lose less.
Okay, I think due to time, we probably should end the talk. And Professor Ma will still staying here around, outside. If there's tea reception, you can still talk to him, and exchange idea. Okay. And let's thanks Professor Ma for the talk.
Thank you.